All right, so then let's get into our concept for today. And today should be a pretty good day for us. We are going to either finish or come very, very close to finishing chapter 4. And so let's look at it from this perspective then. If we go backwards, we ended the ideas on Friday talking about valence electrons and Lewis dot structures and using valence electrons and those Lewis dots to say, here's how many electrons are around this element that are capable of bonding. And we ended with the concept overall here that when bonding occurs, it's going to be because 8 electrons are required for every element. That's the octet rule. And so atoms, elements are going to do something in the way of chemical bonding to get to 8 electrons. They're going to either lose electrons, which is what most metals do, give their electrons away to something else, somebody else, another element. They're going to gain electrons, which is what most nonmetals do, or they're in some way going to share electrons with each other, which is another characteristic of nonmetals. Nonmetals will share electrons with each other. Nonmetals will also take electrons from metals. And those two ideas make up 2 different types of bonding. When we have electrons that are being given and taken, that's ionic bonding. Because in the end, giving away your electrons is going to cause a charge on the metal, and taking those extra electrons is going to cause a charge on the nonmetal. And the 2 charges are going to attract each other. That's going to create the ionic bond. That's ionic bonding. Covalent bonding, we've got the nonmetals sharing electrons with each other. And because they are sharing electrons with each other, they are going to become attracted to each other through that mutually beneficial sharing. So let's look at ionic bonding then first. As we saw in our examples on Friday, metals tend to have small numbers of valence electrons. They tend to have 1, 2, maybe 3 valence electrons. And so in order to get to 8 electrons, they would have to either add 7, 6, or 5 electrons, which would be really difficult. Or they can give those 1, 2, or 3 electrons away and become a charged particle. And that's what they ultimately end up doing. So if I look at it from the standpoint of, say, sodium. Sodium has 1 valence electron, like that. If sodium were to give that electron away to, say, another atom, the end result would be a sodium atom with no valence electrons, but full energy levels underneath it, and a +1 charge because it gave away 1 electron to get there. If I go from 11 protons and 11 electrons to now 11 protons and 10 electrons, that's where I get my +1 charge. Remember, we did some examples of that about a week ago. So that's what happens in sodium. Now, for something like chlorine, if I look at chlorine and its valence electrons, chlorine as a halogen has 7 valence electrons. And so if it adds an electron, say it adds this electron that the sodium was willing to give away, the net result is a chlorine ion with now 8 electrons around it. And that 8th electron, we went from 17 total electrons and 17 protons to now 18 electrons for those 17 protons. We have an extra negative there. We've got a -1 charge on that chlorine. And so as a result, we now have a positive ion and a negative ion. And as you well know, opposites attract. So the positive ion and the negative ion become attracted to each other. And that is ultimately what forms our ionic bond. Now, one important note about ionic bonding. Ionic compounds maintain something called charge neutrality. And what that means is that whatever positive charges are generated by the metals, they have to be matched by an even amount of negative charge by the nonmetals. Because effectively what is happening is that all of those electrons that the metal is giving away are being absorbed by the nonmetal. We can't have any leftovers. And that goes both ways. If I have a metal that only gives up 2 electrons and a nonmetal that needs 3, well, then there's going to have to be something happen so that we use up all of the electrons that we're supposed to. And so that's what we mean by charge neutrality. Every positive charge has to be matched by an equal negative charge, and vice versa. And so not every single ionic bond is going to be a pure one-to-one relationship between the metal and the nonmetal. Sodium and chlorine are, because sodium forms a positive 1 and chlorine forms a negative 1. So those charges do balance each other. They do neutralize each other. But if I have magnesium, which, because it has 2 valence electrons, would form a 2 positive ion, I'm going to need more than 1 chlorine to balance that out. Chlorine's capable of taking 1 of those electrons, but it can't take 2. So it needs a second chlorine ion to take the second electron. The net result is that our magnesium chloride compound has a chemical formula of MgCl2. The second chlorine there is necessary for charge balance. And we don't get charge balance without that second chlorine. It doesn't make sense for magnesium to only give up 1 electron, because that doesn't get it to the octet. Nor does it make sense for a chlorine to take on 2 electrons, because that now gives it 9 valence electrons, which isn't an octet either. So instead, what we see is that we will see multiple interactions. Instead of 1 atom to 1 atom, we'll see 1 atom to 2 atoms, or 2 atoms to 1 atom, or 3 to 1, or 3 to 2, whatever it takes. And so this would be another opportunity if you have your periodic table handy. Based upon the valence charge of your electrons, and based upon the number of valence electrons that you have, we can actually predict pretty well what our charges are going to be. All right, so bear with me 1 second here. I've got to pull up something that the people on Zoom can see. Okay, so last time we did any work on this, we went about labeling our groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Well, now that we know a little bit more about the octet rule itself, we can actually use these same groupings to talk about charge, because if you look, all of the metals we know are going to have a positive charge, and based upon the number of valence electrons had, that's also going to be their charge. So group 1A with its 1 valence electron, it's going to make a terrible looking positive 1. So all of your alkali metals will make positive 1 ions. All of your alkaline earth metals, group 2A, will make positive 2 ions. All of your boron group will make positive 3 ions. Let's skip the middle for just a second. Group 8A, the noble gases, they're already an octet. They do not make ions. Your halogens in group 7A, 7 valence electrons, just 1 away from an octet. -1 charge. Your oxygen group, the chalcogens, 6 electrons, 2 away from an octet, they make a -2 charge. The nitrogen group makes a -3 charge. And then when we come to the carbon group, for the most part, does not make ionic compounds. There are a pair that do, tin and lead. And those two are actually kind of unique because they're more like transition metals. And transition metals, one of their unique characteristics is that they can actually have multiple charges. And tin and lead are no different. Tin and lead could either be +2 or +4. But carbon, silicon, germanium, you're not going to see ionic compounds out of any of them, really. They're all going to be covalent for the most part. So we don't even need to worry about charges on those. Now, why this is important, why we care about this, is because when we get into the periodic table, and when we get into naming compounds like this, all we need to do is find these elements, and we can determine their charges just by where they are on the periodic table. We don't even really need to look at their Lewis dot structure to figure that part out. The Lewis dots help us to explain why they're +1, why they're -1, or whatever their charge actually is. But the periodic table can actually tell us what that charge is. So for sodium, sodium is an alkali metal. In group 1A, it's going to have a +1 charge. Chloride is a halogen. It's in group 7A. It's going to have a -1 charge. To find its chemical formula, here's what we do. If the two charges are the same but have opposite signs, then we just rewrite the formula with those two elements side by side. So sodium chloride would be NaCl. Sodium and chlorine, like charges, opposite sides, we just put them together. The ions essentially cancel each other out. The positive and the negative annihilate each other. Basically, they are attracted to each other, but there is no net charge here. Magnesium fluoride. Magnesium is an alkaline earth metal, so it's got a +2 charge. Fluoride is a halogen. It's got a -1 charge. When the charges are not the same, what we do is something called the criss-cross method. In the criss-cross method, you take the charge, and that becomes the subscript for the other element. So fluorine's charge of -1 means I have 1 magnesium. Magnesium's charge means I have 2 fluorines. The correct formula for magnesium fluoride is MgF2. Yeah, Michael? The charges are not the same. And so when they're not the same, we do the crisscross to make sure that we have a balance of charges. So by getting 2 fluorides, I know I'll have 2 -1 charges, which will balance out the +2 charge on the magnesium. This works in the opposite direction as well. Lithium sulfide. Lithium has a +1 charge because it is an alkali metal. Sulfur is a chalcogen, so it's got a -2 charge. Once again, we do not have a balance of charge, so we need to do the crisscross. The net result is I've got lithium with a 2 and sulfur with a 1. Li2S is the correct formula for lithium sulfide. Again, it's about charge balance here. The sulfur has a -2 charge, so it needs to gain 2 electrons. Lithium can only give it 1 by itself. If I give it a second lithium, that gives us the second electron to make the sulfur. So we can kind of view it, if the picture helps, we can kind of view it this way. If I've got my there are my 2 atoms, lithium and sulfur. If lithium gives this electron to the sulfur, maybe. I have no idea where that went. All right, if lithium gives that electron to the sulfur, yes, it satisfies this lithium. This lithium's now at +1. But notice that the sulfur, while at -1, it's not complete. we need to give sulfur an 8th electron. So what happens is we bring in a second lithium. And that second lithium provides the second electron to make the sulfur complete. And that's how the sulfur ends up with a -2 charge. This is how we get the 2 lithiums for every 1 sulfur in this compound. So again, the Lewis dots can help us to visualize what is actually happening from an electronic standpoint. The chemical formulas tell us what that appropriate balance is. For the last one here, I've got aluminum. Aluminum is in group 3A, so it's a +3 charge. Oxygen is in group 6A, so it's a -2 charge. Again, the charges do not match, so I need to crisscross them. And the net result, 2 aluminums, Al2, 3 oxygens, O3. So Al2O3 is the appropriate formula for aluminum oxide. And again, that comes from that charge balance. I won't draw this one out. It's a little bit more complicated, but you can see, even if I just drew one, why we end up at the answer that we end up with. Aluminum's got 3 valence electrons. Oxygen's got 6. If we fill up the oxygen by taking 2 of those electrons from the aluminum, that takes care of that oxygen, but the aluminum is still left hanging. It hasn't gotten rid of all of its electrons yet. If I pull in another oxygen, that aluminum can give its dot to the oxygen. The aluminum's great, but now that oxygen's not. And so we have to just kind of keep going until we're all even all over. And that's the ratio 2 to 3 that gets us all even all over. Yes. No. I will admit this is a simplification. However, this is a simplification that works pretty consistently for those main group elements that we labeled with the A's. Where we see those exceptions coming in are more in the middle of the periodic table, and we're just not going to deal a lot with too much detail on the middle of the table. The behavior of the main group elements, the ones in those 8 columns that we've been studying, is pretty predictable. And the octet rule is a very, very predictable way of looking at their chemistry. All right, try this out for yourself. We've got iodine and strontium. What I want you to do is just draw their Lewis dots. Draw the dots for iodine, draw the dots for strontium. And then if you need to, draw out the Lewis dot structures for the 3 compounds down here. If you can do it just based off of common charges and doing the crisscross method, all I'm looking for at the bottom here are the chemical formulas themselves. So tell me what the formula for barium chloride is, for aluminum sulfide, for magnesium oxide. I'll come around and check on how you're doing, and we'll probably wrap it here for today and talk about covalent bonding on Friday after the exam. All right, let's see how we did. So for the first one, all I was looking for were just, did you assign the dots correctly? So for iodine, you should have had 7 dots. And for strontium, you should have had 2. Now, some of you took this a step further and recognized that we had a metal and a non-metal and put a formula to it. If you did that, the strontium should have been a +2. The iodine should have been a -1. The correct formula would be SRI2. Now, I noticed walking around, some of you had the iodine first in your chemical formula. Conventionally speaking, that is not how we do it. We usually put the positive charge first and the negative charge second. So SRI2 would be the way that you would see that compound listed out. So again, that's not exactly what I asked you to do, but if you did it, that's what we would have been looking for. For the rest of these, again, we were only concerned with the ionic compound formula. So for barium, we have to recognize barium is an alkaline earth metal. It's in group 2A. It has a +2 charge. The chlorine is a halogen. It's got a -1 charge. The charges are not the same, so we've got to cross them up. We get barium chloride, BaCl2. For aluminum sulfide, aluminum is in group 3A, +3 charge. Sulfur is in group 6A, -2 charge. Again, we got to cross them up. We get Al2, S3 as a result. And then finally, magnesium oxide. Magnesium is an alkaline earth metal, +2. Oxygen is a chalcogen, group 6A, -2. Those charges are the same, positive and -2. So they cancel each other out directly. It's a 1-to-1 ratio. MgO is the result. Now, one thing I want you all to recognize is that this process would work for any of the compounds and any of the ions that we mentioned. So if I wanted to look at the result of barium and sulfur, it's +2 and -2. The formula for barium sulfide is BaS. If I wanted to look at barium and oxygen, it's +2 and -2. The formula is BaO. So this technique literally applies to any kind of ionic compound. If I know the ion's charge, I can figure out what the compound is and what its chemical formula is going to look like. And so that's where we're going to stop for today. Now, exam is still on Wednesday. On Friday, we will pick up the last piece of this puzzle and talk about covalent bonding, which is what happens when those nonmetals share electrons. And that's going to be a lot more dot structure intensive, because the easiest way to draw those out is to literally connect the dots. So we will cover that on Friday. We'll probably get a little bit into chapter 5 as well. Have a great afternoon.